Welcome to the final topic of Module 3, Forensic Toxicology. We will begin by discussing the definition of toxicology as it relates to forensics. We will also discuss how drugs are introduced into the body, how they are absorbed, metabolized, and excreted. We will then discuss the various types of testing that are done on a forensic toxicology sample. Initially, preliminary testing involving immunoassay testing and then confirmatory testing of the toxicology samples. We will determine the amount of alcohol in a specific volume and use the Widmark factor to determine blood alcohol content for specific examples. We will also discuss blood alcohol and breath alcohol testing and how it is conducted in a laboratory, and also several common poisons that may be necessary to be identified through forensic toxicology testing. Toxicology involves the examination of various bodily fluids, tissues, and organs to identify the presence of drugs and/or poisons. There are several different types of toxicology. Forensics toxicology involves samples that are specifically related to criminal investigations, either illegal drug use or possibly death investigations. There is also clinical toxicology, where more therapeutic drug monitoring is performed. Environmental testing of toxicology samples involves effects on air and water sampling. There's also industrial and product development toxicology and regulatory toxicology, which establishes exposure guidelines and helps enact legislation. Toxicology involves testing of either a drug or a poison. A drug is a natural or synthetic substance that's designed to produce different effects on humans. Poisons are substances that have a toxic effect on humans. We examine toxicology samples to answer several questions. Is there a drug or poison present? What is the quantity of that drug or poison? Are there metabolites present from a drug or a poison? And then at what levels of a drug or a poison do they become toxic? This is based on two different principles on how the drugs move through the body and how the drugs affect the body. The pharmacokinetics shows how drugs move through the body, through absorption, distribution, metabolism, and elimination. The pharmacodynamics describe how drugs affect the body. Some of these were the information that we relayed during our solid dosage drug lecture concerning the various drugs. Initially, if we talk about the pharmacokinetics, we will start with the absorption of the drug into the body. This can be introduced to the body in a wide variety of different methods, either through oral, intramuscular, intravenous, rectal, topical, subcutaneous, or inhalation. All methods of absorption are going to involve passage of that drug through some type of a tissue barrier into the bloodstream. So either through the skin, through the stomach, through the small intestines, through nasal passages, that drug is going to be absorbed through the tissue barriers. Once in the bloodstream, the drugs are distributed to every cell of the body. Once it's distributed throughout the body, metabolism is going to begin to occur. This deactivates the drug to produce milder effects. The metabolites are generally more water-soluble, so they can be easily excreted or also easily converted to energy. Most of the metabolism is going to be done in the liver. If we use ethyl alcohol as an example and describe how it metabolizes through the body, it's going to initially metabolize to acetaldehyde, which metabolizes further into acetic acid. This is easily water soluble, so easily excreted in urine or used in the body in oxidation to produce energy. This slide shows how the drug is initially introduced to the body into the small intestines and then absorbed throughout the body, transferring to the liver where it can then be metabolized and excreted. Most drugs are going to be eliminated by the kidneys as urine. However, in some instances, some may also be eliminated through respiration and also through perspiration. When we talk about forensic toxicology, we are talking about human performance samples or post-mortem samples. With the human performance samples, this is going to involve primarily individuals and determining whether or not it involves specific drug use. In post-mortem samples, it would be concerning death investigations to determine was a drug or poison present. It's also important to know the quantity of that drug or poison that may be present, if there are any metabolites present from that drug or poison, and also at what levels that drug or poison are going to become toxic. Human performance toxicology measures the amount or presence of alcohol or drugs in a living person's blood, urine, or breath. The post-mortem toxicology investigates the presence of drugs, gases, metals, and any other toxic chemicals in human fluids or organs, and these samples are always taken after death. So toxicology samples can be recovered from a wide variety of crimes. The collection of toxicology samples usually involves personnel using personal protective equipment and also appropriate containers for the specific toxicology examinations. Usually, laboratories will provide toxicology kits available to hospitals and police agencies that contain the necessary tubes and containers for the testings. Usually a toxicology kit will contain gray-topped blood tubes that contain either sodium fluoride or potassium oxalate. These tubes are used for blood alcohol testing. The kits may also contain lavender-topped tubes which contain the preservative EDTA. These tubes would be used specifically for any drug analysis. The kits also usually contain either a jar or a bottle for urine samples. The collection of human performance specimens may involve various drug cases where blood and urine samples would be collected. It might involve specifically just a blood alcohol case where only blood may be involved in the collection. But in either of these situations, collection should be performed as soon as possible. The collection of post-mortem specimens may involve the collection of various body organs or also fluids that the chemicals would actually concentrate in and then be available for collection during the autopsy. Usually the specimens should be collected before the body is embalmed. In some situations, samples from bone marrow or the fluid in the eye or hair samples may also be tested. All samples that are collected should be appropriately labeled with the name or the initials of the collector, the date and time of the collection, the agency and case number, the name of the individual whose the samples are being collected from, what the sample actually is, where it's being collected, and an item number. And once again, these samples should be appropriately sealed for a measure of security. Before the examinations can begin, once again, we need to be concerned with the chain of custody. So when the samples are initially collected, the date and time, the person doing the collection, all of these things would be documented. When the samples are brought into the laboratory, the chain of custody is also going to be maintained. So the receipt of the exhibit, the packaging of the exhibit, any identifying marks are also going to be noted. This is extremely important, especially with toxicology samples, because it is important to know actually when a sample is collected. In an instance where a traffic accident may have occurred at midnight, but a sample might not have been collected until 8 o'clock the following morning, this would greatly affect the results of any blood alcohol testing that was done and the interpretation from that toxicologist. The samples that are brought to the toxicology section are usually tested for a wide variety of controlled substances, alcohol, or different poisons that might be present, either carbon monoxide, cyanide, or also heavy metals. With controlled substances, that sampling and examination is also going to go through preliminary screenings and then confirmation testing, very similar to what is done with your solid dosage drug cases. In most drug examinations, both urine and blood samples will both be tested from an individual. The preliminary tests are usually conducted by performing immunoassay testing. Immunoassay tests operate on the basis of competition between an enzyme and the analyte in the sample itself. And they are trying to bind to particular sites in pre-coated plates. Once they bind in the plate, then a substrate is added, which is going to cause a color change. The color change is then measured for the absorbance to indicate the presence of a drug. If the analyst obtains a positive preliminary test for a drug, then the drugs are extracted from the body fluids or the organs. This is either accomplished by a liquid-liquid extraction or a solid phase extraction. Both of these procedures were discussed in the Instrumental Methods lecture in Module 2. If necessary, please review this separation method. Once again, it's located in Module 2 under Instrumental Methods. Once the drugs have been separated from the body fluids or the organs, then confirmation testing can be performed by a gas chromatograph with a mass spectrometer. Alcohol testing is probably the most common drug tested within the toxicology section. Since many states have laws regarding the percent alcohol, it's very important to understand a few basics about the drug itself. Most alcohol is sold and marked as a certain proof alcohol. The proof is actually 2 times the alcohol percent. So if a bottle is listed as 100 proof, it is actually 50% alcohol. To find how many grams of alcohol are present in a certain volume, you divide the proof by 2 to get the percent alcohol, and then the percent alcohol means the grams of alcohol in 100 milliliters. So you want to multiply that number by milliliters to get the total number of grams present. If we look at an example and use a brand of vodka that is 100 proof, how many grams of alcohol would you consume if you drank 25 milliliters of this particular vodka? So first, we must divide the proof by 2 to get the percent alcohol. So 100 divided by 2 gives us 50% alcohol. This means that there are 50 grams of alcohol in 100 milliliters. The percent alcohol gives you the grams of alcohol in 100 milliliters. You then multiply the number by the milliliters to get the total number of grams present. So 50 grams of alcohol by 100 milliliters times the 25 that was actually consumed gives you 12.5 grams of alcohol. Alcohol goes through absorption, distribution, metabolism, and elimination, similar to that of the controlled substances. However, when we talk about alcohol, there are several other factors that should also be considered. Usually with controlled substances, a pill may be ingested, but with alcohol, there may be several drinks that are consumed over a period of time. So the rate at which the alcohol is consumed must be considered. Also, the fact of whether or not there is the presence of food in the stomach or not will have an impact on how that alcohol is actually absorbed. The gender and the weight of the individual will also make a difference as to how the alcohol is absorbed, in addition to the concentration of the actual alcohol itself. The specific type of beverage will also affect the absorption, where carbonated beverages are going to absorb faster. Beer will absorb slower due to the presence of carbohydrates, and very strong alcoholic beverages are going to be absorbed slower due to the irritation to the stomach lining. This chart shows the percent alcohol over a time span for various amounts which may have been consumed. So how much can a person drink? There is a general formula that calculates the number of drinks required for a certain weighted individual to reach a specific blood alcohol. However, this does not take into account the gender. The calculation, the equation, is based on the drinks per hour, and this is based on 1 ounce per drink. As you can see from this graph, the presence of food will also have a play into the absorption of alcohol. As will the gender and weight of an individual. To calculate the percent alcohol for an individual use, we can use the Widmark formula. There are different factors for males and females, but if we input the information into this formula, we can calculate the percent alcohol. If we use a 200-pound male as an example that consumes 5 ounces of 80 proof bourbon, we can estimate his blood alcohol content. Initially, you have to determine how much alcohol is present. So initially, you have to break down the 80 proof alcohol to determine that that means 40% alcohol, and then determine using 40% alcohol and 5 ounces exactly how much alcohol is present. You also have to convert the weight of the individual to grams, and then you can input those factors into the Widmark equation to determine that the individual would have a blood alcohol content of 0.075%. If we use a female as an example, you input the information into the equation in a similar manner, however you use a different Widmark factor. So once again, if we use a 120-pound female that consumes 5 ounces of the 80 proof bourbon, we can also estimate her blood alcohol content, and that would be 0.156%. You can see the concentration of the alcohol also makes a huge difference. All of the following contain 0.6 ounces of alcohol. So to obtain 0.6 ounces of alcohol, you can actually consume more beer than you can hard liquor. There are 2 different testings of methods for alcohol analysis in a forensic laboratory. It depends if you are doing blood alcohol content or breath testing. The testing for alcohol can be done by either method. With the blood alcohol content, there is a given temperature that the amount of alcohol in the air of a contained vial will be the same for the amount of alcohol in the blood. So an analyst is able to obtain a headspace from the vial itself and then expose that to a gas chromatograph that has a flame ionization detector to determine the amount of ethanol that is actually present in a sample. For breath testing, the analysis is done slightly different. Since alcohol is in the blood, it also circulates through the lungs. Oxygen is eliminated from our body as carbon monoxide through our nose and mouth. The alcohol is also eliminated in a similar manner, so it can be detected by breath testing. The breath testing is done with an infrared spectrometer, and the alcohol will absorb at a particular wavelength. The key to breath testing is that the person doing the test must wait approximately 20 minutes and keep the individual under close contact. They need to take an extremely deep lung breath when the test is actually being conducted, and usually these are done in duplicate test. In the toxicology section, there may also be testing done for various poisons, the first of which might be carbon monoxide testing. Carbon monoxide is colorless and odorless and tasteless, but it's going to be produced in many combustible processes, so its exposure can be accidental or intentional. The testing of carbon monoxide is done with a CO oximeter, which measures the absorption at several different wavelengths to distinguish various forms of the hemoglobin. Cyanide may also be tested in a forensic toxicology section. Usually this test is performed on a sample by using a simple color test that will turn blue when it's acidified with an acid. Other metals may also be tested in forensic laboratories, and specifically some samples besides blood and urine may also be tested. Things like hair samples, nail samples may also be tested using some of the other instrumental techniques which we've discussed. Once the drug or poison has been extracted and identified, the toxicologist may also be required to provide an opinion as to the drug's effect on an individual person's performance or physical state. There are well-documented levels of the observable effects of alcohol on an individual. So at times they may be asked to determine what a blood alcohol level was when an accident actually occurred. Metabolism occurs at a rate of 0.015% per hour. Alcoholics may have a slightly higher metabolism rate. So you can keep in mind to be able to determine the blood alcohol content when an accident occurred from readings that a sample may give.